Hey, Mr. Leong, finally, the marble sequence is here. They're looking for Asian Thor.
Oh, wow. Okay, finally, right?
Yes, I'm going for audition later today, you know?
You doing your teacher?
No, I'm not teaching anymore. I just want to be Thor.
Okay. Can you pose like him first?
Can, no problem. See, do I look like him? Am I tall enough?
I think you're not that great, leh.
Cannot.
Yeah, I think you need an additional booster.
Really? You can help me?
Can.
The chemistry way?
The chemistry way, correct.
Okay, come, let's do it.
Now, huh? Okay.
Yes, come, let's do it.
I got a simple cell.
Okay.
Whoa. Wow, I think you really can make it now, leh. Yeah, we'll see you in Asia Tour later.
Yes.
Wow, Mr. William, how was the audition?
Oh, it was great, you know. Thank you to your lemon.
Oh, okay.
Yeah, because of it, I became Thor-like,
Okay.
and I'm going to be the lead actor for the next Thor sequence.
Oh, congrats, don't you teach already lah?
Yes, it's coming in 2049.
Oh,
Wait for
nice.
it.
Okay, 2049.
Yeah,
Wait for
so
it.
how does it work?
The lemon.
Yes.
Okay, so what's happening in this lemon itself is that there's actually a redox reaction happening, and this redox reaction is helping me to generate electricity.
I see. So redox reaction can actually generate electricity.
That's
maybe
right.
Thor-like.
Correct.
Oh.
So we can actually see this from the lesson that we learned last week. It can be represented through a diagram. So as we move on to the encyclopedia, this is what you're going to see. So in simplified version, this is going to be a typical setup of a electrochemical cell. It is made out of two half cells, one on the left and one on the right. And one of the things that you have to do over here is to understand which half cell is undergoing reduction or oxidation, right? Yes. So in this case, we are connecting a zinc as well as a copper. From secondary school, we already learned that zinc is definitely more reactive than copper. So zinc is the one that's going to undergo oxidation. So there we have it, oxidation. On the other hand, your copper 2 plus is going to undergo reduction.
Yes, that's right.
These two half cells are connected through a external circuit, and this circuit has a voltmeter over there. So Mr. William, what's the purpose of a voltmeter?
I think the voltmeter is to tell us how much electricity is being generated.
Sure. So in this case, it's from one side, and on the other side, right, we need to connect these two half cells using this thing called a salt bridge. So Mr. William, what's a salt bridge now?
Well, a salt bridge basically it comprises of ions of different charges, right? So in a salt bridge, typically there will be a combination of cations as well as anions. So I'm going to label positive as well as negative ions. Now the main function of a salt bridge, if you guys remember, is to do this thing which is to maintain electrical neutrality.
That's right.
Right. So why is there a need to do so? You have to look at individual half cells to begin with, right? So if we focus on the left-hand side, now Mr. Leong, can you tell us, focusing on the electrolyte, what's going to happen to it? Does it get more plus? Does it get more minus?
So we're producing more zinc 2 plus, right? Obviously, the solution will have an accumulation of positive charges.
That's right, right? So you can see as time progresses, my solution is going to experience a buildup of positive. Whereas on the other side, you do notice that reduction is taking place,
right.
which means your copper 2 plus is being consumed, right? So what's going to happen to the solution?
It feels like there's less and less positive charges, so we can think of it as there's more and more negative ones, right?
Right. So you can see there's a buildup of negative on the other side, and this is electrically not neutral, right? So what a salt bridge is supposed to do is to cancel this buildup of charges. And just remember that opposite charges, they will neutralize each other.
That's right.
So if plus is building up on the left-hand side, then the negative ions from the salt bridge will enter the solution to counter away the buildup of plus. And likewise, the positive ions will enter the solution on the right-hand side. So this way, it will help to maintain electrical neutrality. Right, so this is the main function of the salt bridge, in addition to the fact that it is going to complete the circuit.
That's right. Okay, so the other thing that's quite important for us is to look at each of the individual electrodes. So these are the metals that are connected to the electrolyte. These are where your redox reactions are going to happen.
Yes.
So one of the things that we do is to name these electrodes. So if on the left-hand side, the half cell, it is undergoing oxidation. So Mr. William, can you remind me again, this is going to be the cathode or the anode?
Oxidation is always the anode.
Okay, so I'm going to put here the anode. And can you tell me, do you think this with the plus or the minus terminal?
Well, you have to look at what happens in a reaction, right? As you can see from the equation, electrons are being produced, right? So I'll call this like the supply,
Okay.
right? So if you supply negative, then you yourself should be a negative terminal in nature.
Okay, sure. So I'll put a negative terminal over here, the polarity, which must mean that the other side is all going to be the opposite, right? We're going to call this the cathode because reduction has occurred. And of course, this is going to be the plus terminal.
Correct.
Okay?
You're taking in electrons. You're
That's right.
demanding for electrons.
So I'll go put here demand over here, right? And because you see that the electrons are on the left, it is absorbing in the electrons. Okay. So one of the easy ways that I used to remember, right, is that this is reduction and this is a cathode. So I usually use the acronym REDCAT, right? Reduction is always at the cathode. Okay. Last question for you, Mr. William. I want to see in this external circuit over here, how are the electrons flowing? Can you shed some light on that?
Can. Econs. How do goods flow, right? From the supply to the demand. Exactly the same for electrons.
Okay, so it's always coming out from the anode and then it moves towards the cathode, right? So that is going to be the flow of electrons. So what we have seen just now is actually connecting two half cells together, right? And when we connect them, electricity is going to flow. The voltmeter is going to register this thing called a potential difference, okay? To really investigate this value over here, I think it's more meaningful to look at just one half cell only, right? So what do we normally do with this one half cell?
Well, you have to match this against a reference for the values to be meaningful. Right? So maybe let's talk about the reference first.
Sure. So in our syllabus, our reference is known as the standard hydrogen electrode, or in short, I just call it the SHE. So the equation is going to be this one. Your H plus ions are going to get reduced to H2 gas, right? So in a half cell, it is important to have all the species that are present. So if I take a look at the setup over here, we're going to start off by using a inert platinum electrode, and we're going to dip this into the electrolyte, which is going to be my H plus ions, right? And the word standard over here means that there are certain rules that I have to adhere to, right? So the concentration, Mr. William, must be?
It has to be 1 mole per dm cube.
1 mole per dm cube, right? And of course, when we feed in the gas, which is the H2 gas, we're going to feed it in through a inverted test tube, right? And in this case, they must have certain conditions. What are the standard ones again?
298 Kelvin as well as 1 bar.
That's right. So these are the standard ones that you must always remember. Okay. So of course, we're going to connect this to the half cell of interest. Mr. William, can you run us through that?
Yep. So it really depends on what you are trying to measure against. Once the reference SHE is done, right, we look at the right-hand side of your notes, right, there are different types of setup. So if you go down a little bit to your notes, you will see that generally there are 3 different types of examples that we have encountered. Now, the first one will be a metal together with its aqueous ions. So for example, if I'm trying to measure between copper as well as copper 2+, what you do is to make that metal, the copper, the electrode of this reaction. And then your copper 2+ will be inside the solution, Cu2+. Obviously, you have to stick to standard conditions, which is 1 mole per dm cube. Now, sometimes you may have a combination of gas together with its aqueous ions. So Cl2, Cl minus, very good example. So Cl2, make sure this is pumped in at 1 bar and 298 Kelvin, and then your Cl minus will again be inside the solution. But you do notice, right, in this case, the electrode is platinum.
That's right.
Right. So why do we use platinum?
Because if you take a look at the half equations, there is no metal at all, right? So we have to use an inert electrode so that they don't participate in the half equation.
That's right, right? So in this case, we use platinum because it's inert. Now, on the right-hand side, you do notice sometimes you may have aqueous ions in different oxidation state, like iron 3 as well as iron 2. So what's going to happen, we expect both of them to be inside the aqueous solution of 1 molar each. Now, usually, Mr. Leon, there's a common mistake, right, that people make. What is that mistake?
It's the same thing as you were saying. The electrode, people like to put iron, right? Because they see so much iron, so everything must be iron. Yeah, but what's the problem with that?
If iron is there, then what's going to happen is iron is going to take part in the reaction itself, right? But we don't want iron. What we want is really a reaction between iron 3 and iron 2. So you have to be careful. Don't have iron inside. Rather, you replace the electrode with something that's inert, right? Which is going to be platinum. Okay, so do take note, common mistake that people will make. Right, now that you've seen the different examples of half cells, so what we will do, going up a little bit, is to connect this thing against our reference, which is SHE, and this voltmeter is going to register a potential difference or reading over there, which is what we define as the standard electrode potential. Right, so you can see roughly the definition. Okay, please know this because they will ask you straight in the face, what's the definition of this? So we put an asterisk on this. It is the potential difference between whatever half cell you're trying to measure as well as the reference of SHE, and everything has to be done under standard conditions.
So after measuring the E0 value, right, connecting it to SHE, we get a reading. I want to know what does this reading really mean, right? So we're going to take a look at 2 examples. These are 2 examples that are lifted off from the data booklet. Okay, so I have a silver, which has an E0 value of 0.80, a positive value. Aluminum is the other one, which has a negative value, right? One is more positive, one is more negative. Mr. William, what do you think is the significance of these values?
The plus or the minus, basically what E0 value stands for is the likelihood of reaction occurring in a forward direction, which is going to be reduction in this case. Right? So if I see a plus 0.8, plus means it's likely for the forward reaction to take place.
Oh, okay.
Yeah, and if there's a minus, it just means it's very hard for the forward reaction to take place, which conversely, what does that mean?
It probably means that the backward reaction is more likely to take place. That's right. So if I take a look at the direction of the arrows, right, the forward reaction, when I write it in the data booklet form, right, the electrons are on the left, which means that this is going to be a reduction. So in this case, a more positive value indicates that reduction is more likely to occur. And conversely, a negative value favors the backward reaction. The backward reaction is more enhanced, which is simply the oxidation one. Right? So in general, the E0 value, the higher it is, the more reduction is going to happen. Right? So this is something that we have it in the box over here. So this is something that you really have to know very well. So let's take a look at the electrochemical cell again. Okay, so we're done with looking at one half cell. We're going to connect two different half cells together, and it's to generate me a simple electrochemical cell. Okay, so we're going to go for a bit more exam skills. The first thing that you have to do when I present you with a question like this is always to determine who is undergoing reduction, who is undergoing oxidation. And Mr. William, how do we do this?
Well, let's look at the diagram together.
Yes.
So you can see on the left-hand side, we have N2O together with NO3 minus, right? So the very first thing that we will do is to simply go to the data booklet, blindly copy down the E dot values, which is something that we have done here, plus 1.11. And then on the right-hand side, you will notice we have silver and silver plus, which is 0.8. Now, do realize both of them are written as reduction.
Yes.
But it cannot be both doing reduction,
Of
right?
course.
It has to be one guy oxidation, one guy reduction. So the rule that we learn is the more positive will favor the reduction reaction.
That's right.
Which is the one on the left-hand side.
That's right. So I'll put
let's
reduction
label,
here.
Yep, the
And
reduction.
then this is going to be the oxidation, right?
Correct.
Okay.
Then flow, right? Let the thoughts flow. If it's reduction, it becomes the?
Is a cathode, because I think of red cat, right?
Yes, it's a
So this is, I'm going to put a cathode, and
Alright.
which means that on the other side, it must be the anode.
Yep.
Yes.
Okay, then before we move on, we have to look at the charges of the electrodes, right? So the anode is, remember, the place where you give out electrons.
That's right.
So it's the supply, and the supply becomes
Negative.
negative, right? On the other side, then there will be the cathode, and the cathode will be the demand for electrons. This is the positive terminal.
That's right.
Right, so before we start, this is always everything you do first. Make sure you have a good idea who gets reduced, who gets oxidized. Label everything first.
Yes, even before looking at the questions, right?
That's right.
Yeah. So one of the things that also is important is to take a look at the flow of electrons. So remind me again, Mr. William, flow from where to where?
It's always from the supply to the demand or from the anode towards the cathode.
That's right. So it's going to move in this manner. Okay. The other skill that's important for us to pick up is we're going to calculate what is the value that you see at the voltmeter, and that is what we call the E cell value. That is measuring the potential difference between the two half cells. So there's always a standard formula. It is always going to be E reduced minus E oxidized, right? So you simply take the E naught values from here, minus away the E naught values from here. You will always end up with a number that is positive. Okay. Now, E cell has a different kind of significance. If the E cell is positive, Mr. William, what does that mean about the reaction?
It means that the overall reaction is going to be a spontaneous reaction.
Yes.
It means it will take place on its own.
On its own, right? Yes. So for electrochemical cells, you'll notice that because of how we find out the reduction and oxidation values, the E cell value will always be positive, which simply means that electrochemical cells are always spontaneous. It will always automatically release you electrical energy.
See you in class!